Our third speaker before the break is Virginia Smith. She is a third-year PhD student in the AMP Lab. Her background's in machine learning and optimization. And she'll be talking about some recent and interesting work on distributed optimization for common machine learning algorithms, or models.
Hey everyone, thanks. My name is Virginia Smith. Like Amit said, I'm a third-year PhD student. Today I'll be talking about Coco, which stands for Communication Efficient Coordinate Ascent. And this is an algorithm that we've developed for large-scale optimization. So this is joint work with some collaborators in the AMP Lab and also some folks at ETH Zurich. So here's just a brief outline of my talk. I'll start by introducing large-scale optimization. So what is that and why is it important? I'll talk about Coco, the method that we've developed, and share some results. Okay, so the motivation for this project comes from the fact that there are many people, researchers, companies interested in solving machine learning problems with very large data sets. So here are some examples of some of those players and some of the problems that they might be interested in. And what's a typical workflow like for people who are trying to solve these problems? Well, you start with your data set and the problem that you like to solve, for example, classification. And there's important steps that you need to take next, which Evan will be talking about in detail in the next section, like featureization. But underlying this, you'll have a machine learning model that you select, like logistic regression. And a really important step here is that the way to solve these models is by solving an optimization objective. And so the way that we do that is by using an optimization algorithm. Okay, so just to make this very concrete, let me go over an example. So suppose that we'd like to use a support vector machine to solve a classification problem. So say that we have, for example, the MNIST data set, which is kind of been used a lot. This is a data set where we would like to classify these different images based on what digit they are. So for example, we have some 2s on the left versus some 8s. And we can represent these images as data points in some feature space. So for example, we have these red points, which are 2s. These blue points are 8s. And the support vector machine says we like to find a separating hyperplane between these points that has as large a margin as possible. But the point that I really want you to get out of this is that underlying this is an optimization objective that you need to solve in order to fit your model to the problem. And in the single machine, there's tons of methods that you can choose to solve this problem. In fact, there's so many methods that there's actual packages that have been developed just for solving this specific problem. But what happens when you have very large data? Well, there's really another important component of this workflow, which is what system setting are you in? So are you in multi-core or cluster? Are you on the cloud? Because that really has a big impact on what optimization algorithm you use to solve this model. And in fact, it's an open problem to know how to efficiently solve a specific optimization objective when your data is distributed across multiple machines. So when your data is so large that it must be distributed across multiple machines. So what are some things that people attempt to do in this setting? Well, one perhaps naive thing you can imagine is if you have your data spread across multiple machines. So here, imagine that we have these k different machines represented as these squares, and we have our data points, which are just the gray rectangles on each of the machines. You can imagine at each iteration picking a single data point and computing an update with respect to that data point, and then passing that update to the master. And once you pass that update to the master, you add that update to your parameter vector, and then you pass that back to the machines. So this sort of iterative process says, let's always be communicating between the machines and the master. It's nice because we have convergence guarantees about this type of algorithm, but it's obviously not ideal for the distributed setting because we're communicating all of the time. Has very high communication. So this is sort of a spectrum. What can we imagine on the other side of the spectrum? Well, instead of constantly communicating with the master, you can imagine just completely solving each of these sub-problems on each machine, and then doing something like averaging the final result back on the master. So this sort of paradigm says, let's never communicate, or let's communicate only once at the very end, which is nice because it has very low communication. And in fact, there are folks in our lab who have shown specific problems for which this type of algorithm does converge. But an issue with it is that convergence is not, in general, guaranteed. So what else can we imagine? Well, there's something sort of in the middle, which is instead of processing a single data point, you can imagine processing a few data points on each machine before you communicate back to the master. So this is what is known as the mini-batch framework. So at each iteration, you go and you compute your updates with respect to a few data points. Then you pass those back to the master and you apply them. And what you're doing here is you're taking an average over the batch size B. This is great because we have convergence guarantees about this algorithm. And the communication is also tunable. And what I mean by that is you can choose the batch size to be as large as you'd like to balance the trade-off between communication and computation in your setting. So this is sort of a natural middle ground, and it's very common, something that people are using a lot now. So we may wonder, in this setting, are we done? But in fact, there are several limitations to what is currently being done with mini-batch optimization algorithms. One is that the most common algorithm used is stochastic gradient descent. And we may wonder, are there methods beyond SGD that may perform better? Another is that the updates themselves are somewhat stale. And what I mean by that is that when you go to compute the updates on each machine, you don't actually end up applying them until you send them back to the master. And so can we do better than that? Could we, for example, apply them immediately on each machine locally rather than waiting till we communicate? And the last thing is that, like I said, we're taking that average over the batch size. And this can be bad for the following reason, which is that you're making these updates and you're taking some step progressing to the optimal solution, and then you have to divide by the size of the batch. So that is sort of cutting you back. It's sort of cutting back the progress you're making. So can we do something better than that? And this sort of tees me up nicely to talk about Coco, because these are the three limitations that we really addressed when developing our algorithm. So instead of using stochastic gradient descent, we're using a primal dual framework that allows for multiple optimization algorithms to be used internally. Instead of having stale updates, we're immediately applying our updates locally on each machine. And instead of averaging over the batch size, we're averaging over the number of workers, K, which is strictly less than the batch size. OK, so these are sort of the principles of Coco, which, like I said, stands for Communication Efficient Distributed Dual Coordinate Ascent. And so I'm going to talk about each of these sort of three things that we changed in a bit more detail. The first is that we're using this primal dual framework. So what do I mean by that? You can solve a problem in its primal objective, or you could consider solving an alternative problem, the dual. And the dual is a lower bound on the primal. It has several nice theoretical properties, and it also gives us good performance in practice. So for example, this is the default in software packages like liblinear. OK, like I said, we're immediately applying updates. So a stale update would look like this. We're going out and we're computing all of the updates for each of the points in our batch size, but we don't actually apply them until we communicate them back to the master at the end of this sort of for loop. A fresh update would instead apply the update directly after it's computed. So this is what we're doing locally on each machine. And finally, like I said, we're averaging over the number of machines K instead of the batch size. So this is sort of allowing the updates that we make to go a bit further. OK, so here's the algorithm in all of its glory. I don't really want you to take anything out of this slide except that it can easily be shown on one slide. It can actually be written in less than 10 lines of code in Spark. And like I said, it's a primal dual framework. It allows for any internal optimization method to be used. And two of the major updates that we're making to this algorithm to make it more communication efficient are we're applying updates immediately on each local machine, and we're taking an average over the number of machines K. So these are sort of perhaps intuitive changes to make, but it's, of course, very difficult to show that this still converges in practice. So this is our convergence result. What I want you to get out of this is just that it does converge, and we've shown convergence rates that match current state-of-the-art mini-batch methods. So given that our rates are matching the current state of the art. You may wonder, why would anyone use this in practice? And for that, I'll show you the results that we have. So these are some empirical results in Spark. So we looked at several classification data sets, and we looked at solving a support vector machine for these data sets. And these data sets differed, on the number of training points, as well as the features and the sparsity. So here's an example of one of the results. This is for the ImageNet data set, which is attempting to classify images. And what you see here is that on the x-axis, we have time. On the y-axis, we have how close are we to the optimal solution. So we'd like to be getting down to the bottom right-hand corner of this graph as quickly as possible. Coco, our algorithm, is shown here in red as compared to 3 other state-of-the-art mini-batch methods. And you can see that Coco is really converging to the optimal solution much faster than the 3 other methods. And in fact, this was true for all of the data sets that we looked at. So you can see in all of these plots that the red line, which is Coco, is converging to the optimal solution faster than the other methods. OK, so with that, I'll just give a summary of what we talked about today. So some takeaways are Coco is a framework for distributed optimization. And as we talked about, optimization is really at the heart of solving a machine learning model. Coco uses state-of-the-art primal dual methods, and then it drastically reduces the amount of communication necessary to implement these methods. We have strong empirical results, as well as convergence guarantees for this method. And I'm not sure we'll have time for one question, but please feel free to come talk to me during the break. This work will also be appearing at the Neural Information Processing Systems Conference in December. And check out my website if you'd like to find a link to the paper, and we'll be releasing code before the NIPS conference as well. So check that out. Thanks. Oh, he was asking, do we identify which of our changes led to that fast convergence? Yeah, so using the primal dual method itself only gets you so far. So some of the methods that we looked at were using those primal dual methods, but without the changes that we made to communication. So we really believe it's this fact that we're able to apply these updates immediately on each local machine that we're. Yeah, yeah. Great. Thanks.
Great. All right, so let's thank our speaker again. All right, so we have a break right now. Also, there's going to be a fire alarm going off, so if you hear some loud, weird noises, don't be alarmed. That actually, though, is coinciding with our break, so it shouldn't change our schedule very much. We might be pushing back 5 minutes or so. We don't want to start talks during a fire alarm. All right, but yeah, take some time, chat with the speakers, get some coffee, and we'll be back in 15 minutes.